This is a brief lecture over the structure of the atom and introduces the concept of isotope. We had this slide on the last pre-recorded lecture. It's a summary of the subatomic particles in an atom, and I'll mention again that there are even smaller subatomic particles. There are things called quarks within protons and neutrons, which we won't go into in this course, but I just want you to be aware of it. So again, the three subatomic particles are the proton, or the three basic ones, proton, neutron, and electron. The proton and the neutron are located inside the nucleus. The proton has a positive charge, the neutron has no charge, so the nucleus overall has a positive charge because of the protons. Outside the nucleus we have the electrons. They have a negative charge, and the mass of the electron for our purposes is going to be considered to be negligible. We're going to just assume it's zero even though it's not. The mass of the protons and neutrons are about equal to each other, and we're not using grams when we talk about mass of on an atomic scale. We use units that AMUs, they stand for atomic mass units, and it's just a scale that scientists made up for very small masses. Alright, so the first thing we're going to learn about is that the number of protons in an atom identifies what element it is, and so that's called the atomic number. The periodic table is actually arranged by atomic number, so you have hydrogen that has an atomic number of 1, which means it has 1 proton. Then of course you have helium with an atomic number of 2, which means it has 2 protons. So all elements are identified by their atomic number or the number of protons. That's probably the single most important piece of information to get out of this lecture. We have symbols that we use to identify an element, and this is the basic type of a symbol that you'll see on the periodic table. Each element has a little square, and at the top is the atomic number, which remember is the number of protons. The bottom is the atomic mass. In the middle is the atomic symbol. All atomic symbols will either be 1 letter or 2 letters. If it is 2 letters, let's say like calcium, the second letter is always lowercase. Alright, so this is kind of a brief introduction to isotopes. It turns out that almost all elements have multiple versions of the element, and each of those versions is called an isotope. What is an isotope? Isotope is an atom with the same number of protons, which means it's actually the same element, but it has only different number of neutrons. Okay? Neutrons does not change the element, it only changes the mass. Okay? So if you see something that has the same number of protons but different number of neutrons, that is an isotope. Here's an example. Carbon actually has 3 isotopes. Only 2 of them exist naturally on Earth. The carbon-14th, which you've probably heard about, is in the upper atmosphere. Okay, so we don't see much of it. Well, we don't see it existing naturally on our Earth. But anyway, I'm going to talk about all 3 isotopes of carbon. As you can see, the atomic number for all of them is 6 because the element carbon has 6 protons. They do, however, have different masses. This is their mass number. And they have different masses because they have different number of neutrons. Carbon-12 has only 6 neutrons, carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons. So The sum of the number of neutrons and protons is called the mass number. You may have heard me on the last slide refer to the mass number of the 3 different isotopes of carbon. In the symbols that we use on pen and paper, the mass number goes in the upper left, the atomic number in the lower left. Whoops. I want to take a minute and compare this symbol that we use on paper to the symbols you see in the periodic table, because they're a little different. If you go back a couple of slides, I just told you that symbol, let's just use carbon again, on the periodic table would look something like this. Okay, the box for carbon in the periodic table. And if you look the symbol for carbon on paper, or if you wrote it on paper, it would look like this. Let's compare those for a minute. What's the difference? You might notice that the atomic number on the periodic table is on the top. The atomic number, if you see a symbol in a book or written on paper, is on the bottom. And on the periodic table, the atomic mass has decimals, usually. And the mass number, when using pen and paper, is a whole number. What's going on? So for right now, I simply want you to be aware of the fact that the symbols for elements are different on the periodic table compared to when you read them in a book or on a piece of paper. And the next couple slides should describe why that is. There's actually a good reason for that. But right now I just want you to be aware of it. So before you leave this page, you should make sure that you understand what mass number is. Okay? It's when you add together the number of protons and the number of neutrons. And it appears in the upper left of a symbol that's written on pen and paper. You need to understand that mass number and atomic mass are different from one another. They're similar, they're related, and I'll explain it in a minute, but they are different. The mass number refers to the mass for a particular isotope, in this case, carbon-12 isotope. The atomic mass, which shows up in the periodic table, is an average of all the isotopes. The atomic number is the other thing you need to make sure that you understand. That's simply the number of protons. That's how the periodic table is arranged, by atomic number. And the atomic number is also what defines an element. So how do you find neutrons? We have a mass number, which is protons plus neutrons. And we have an atomic number, which is just protons. So how can you find neutrons by looking at a chemical symbol? Simple math. If you have protons and neutrons and you subtract from that the number of protons, what do you have? You have the number of neutrons. So let's look for a minute at the isotope carbon. The isotope carbon-12, if we were to write its symbol again, would look like this. We know that the 12 is the mass number for this isotope, and that 6 is the atomic number. We also know that mass number represents protons plus neutrons, and the atomic number represents just protons. So if I were to ask you to find the number of neutrons in the isotope carbon-12, you would simply subtract the atomic number from the mass number. So 12 minus 6 is 6. So that would mean there are 6 neutrons in the isotope carbon-12. Pretty easy. And that is why on pen and paper we write the symbol for elements with the mass number on top and the atomic number on bottom. So it's set up just like a normal subtraction problem. So here's an example for you to try on your own. Magnesium has 3 different isotopes, and they're referred to as magnesium 24, magnesium 25, and magnesium 26. Using the rules that I gave you on the last 2 or 3 slides, write the complete chemical symbol for each of these 3 isotopes and determine how many neutrons are in each of the 3 isotopes. Remember the definition of isotope. It's atoms that are of the same element, therefore they have the same atomic number, and they have different number of neutrons, therefore different mass numbers. What I would recommend doing at this point is turning the video off, seeing if you can do this on your own, and then turning it back on, and I'll go over the answer for you. So here's the solution on the problem that was just presented about the 3 different isotopes of magnesium. The rule is, if you have an element, the mass number goes in the upper left, and the atomic number goes in the lower left. So hopefully you were able to do that with magnesium. So the 3 isotopes of magnesium, the first one had a mass number of 24. So this is the correct symbol for that isotope. Magnesium 25 has a symbol like the one in the middle here, and magnesium 26 on the far right. So as you can see, they all have the same atomic number of 12. They all have 12 protons. They have simply different masses. As far as finding the number of neutrons in each of these 3 isotopes, just remember that these symbols are set up like simple math problems. So you simply take the mass number and you subtract from it the atomic number, and that will give you the number of neutrons. So magnesium 24 has 12 neutrons. Magnesium 25 has 13 neutrons. And magnesium 26 has 14 neutrons. Not hard. This is the type of problem that will show up on your quiz, and a key thing I expect you to understand and be able to do with isotopes and atomic symbols. There are a couple of different ways that isotopes are notated or shown, and the additional ones besides the symbol that we just went over are shown at the bottom of the page here. So if we were talking about neon 20, we would be referring to an isotope of neon with a mass number of 20. Okay? So that's important that you don't get confused. This number that appears after an element name is not the atomic number, it's the mass number. So there we go, that's neon. Another way to do that, instead of using the symbol, might be to actually write out the name of the element. So again, the thing to remember here, if when you're reading you see either a symbol of an element or the name of an element followed by a hyphen and then a number, that number is the mass number. It turns out that each isotope of an element appears in its own natural abundance or percent compared to all the other isotopes of that element. Some of the isotopes are more stable than the other, and so they're present in a higher abundance or higher percentage on our Earth. So let's look, for example, at the 3 natural isotopes of neon. We have neon 20, neon 21, and neon 22, and their abundances are really different. Okay, the most abundant by far is neon 20. That is the most stable of the 3 isotopes. The other 2 isotopes of neon are present in much smaller amounts. So what scientists did when they were making the periodic table, they asked themselves a basic question. Which mass do we report for neon in the periodic table? If you don't want a periodic table that shows every single isotope of every single element, you need to somehow represent the conglomerate or the mix of isotopes. And so scientists decided to take an average mass of all of the natural isotopes of an element. So the question is, do we take a simple average of the masses, in which case we would get 21 for the mass of neon, or should we also take into account the fact that each of these isotopes is present in different abundances? Scientists decide that the overall average mass of an element should be related to how much of that isotope is present. And so they came up with a formula for what we call the weighted average atomic mass of each element, which averages the masses of each isotope, but also weights each of these masses by how much of that isotope is present. So let's look at an example. There is a formula that we use to calculate average atomic mass. Okay? And basically what it is the abundance of an isotope in fractional, that is decimal form, not in percent form, times the mass of that isotope. So if you look in the back slide, the last slide, you can see that the percentage of neon 20 was 90.48. So remember, this equation looks for the fractional abundance. So the fractional abundance of neon 20 is 0.9048. Okay? And the mass of neon 20, of course, is 20 AMU. That's for the first isotope. You do that type of math for each of the isotopes of an element. In the case of neon, there would be 3. The fractional abundance of neon 21 is 0.27. Its mass, of course, is 21 AMU. And then the third isotope of neon has an abundance of 0.0925, and its mass is 22 AMU. I want to take a moment to point out a really common error that students make. That third isotope, neon 22, had a percent abundance of 9.25. Be really careful when converting that to fractional or decimal abundance. Remember that anytime you go from percent to decimal form, you need to divide by 100, which means you need to move the decimal point over 2 places to the left. What I see a lot of students doing in a number like this is accidentally writing 0.925, which is wrong, instead of 0.0925. Just double check yourself on these very small percentages. It's really easy to accidentally drop a 0. So then what you would do to find the average atomic mass of neon overall as an element is you would complete this mathematical equation. And you would get the number that appears at the bottom of neon on the periodic table. Here's an example for you to try on your own. Turns out that chlorine has 2 naturally occurring isotopes, chlorine 35, chlorine 37, and use the formula that I just gave you for average atomic mass and go ahead and calculate the average atomic mass of chlorine. I would recommend stopping this video and then turning it back on to check your answer with mine. Alright, so using the formula for the average atomic mass, let's go ahead and see how we calculated that for chlorine. I would first like to point out that in a lot of these problems you might see the possibility of using 2 different masses. For example, they showed you symbols for the 2 isotopes of chlorine, chlorine 35 and chlorine 37. And so you might ask yourself, well, why can't I just use the number 35 in the formula and the number 37? Why am I using these really precise decimal forms? If given the choice in a problem to use a rounded value or a much more precise value, go ahead and use a more precise value. And since they gave those to you here in this problem, that's what you want to use. So again, make sure when you're plugging in for the formula average atomic mass that you convert the percentage abundances to decimal form by dividing by 100. When you calculate this through, again, carry too many sig figs until you get to the end. Don't round until the very end. You will see that the average atomic mass for the element chlorine is 35.45 AMU. If you look at the periodic table, that is the number that appears on the periodic table. One of the things you may not have noticed and that might help you in some of your homework, mastering chemistry homework, is the average atomic mass that appears in the periodic table will be closer in value to the mass of the isotope that is more abundant. Did that make sense? Let me say it one more time. The average atomic mass that you see in the periodic table at the bottom of each element symbol will be closer in value to the mass of the isotope that is most common or most abundant. So what you can tell by looking at the average atomic mass of chlorine is that of the two isotopes of chlorine, the isotope chlorine-35 is the most abundant because the average atomic mass is closest to the 35. That's just kind of an important, useful little tidbit to have. That's it for this lecture.